For introduction for application of differentiation, first of all, I want to tell you what is the maximum and minimum in differentiation. In calculus, maximum and minimum points plays a significant role in determining the behavior of function. The process of finding these points involves differentiation, especially using the first and second derivative test. By analyzing the behavior of a function derivative, we can identify where it attains its highest and lowest values, known as maximum and minimum points respectively. When and why do we apply this? Maximum and minimum problems are important in various fields of mathematics, engineering, economics, and optimization. These types of problems involve finding the highest or lowest value of a given quantity within a specific set of constraints. By solving maximum and minimum problems, we can optimize our decision, allocate resources efficiently, model real-world situation accurately, and gain a deeper understanding of mathematical concepts.
Now we will move to the situation example. Lisa owns a property with a spacious rectangular swimming pool covering an area of 1,000 square meters. Seeking to enhance the privacy and the security, she plans to enclose the pool area with suitable barriers. Opting for accommodation of materials, she decides to construct a brick of wall along one side costing Rm 30 ringgit per meter, while utilizing a metal fence on the remaining three sides priced at 10 ringgit per meter. This choice strikes a balance between privacy and visibility, ensuring the pool remains protected while maintaining an open and ventilated atmosphere. Lisa carefully calculates the required quantities of material based on the pool's dimension, determining the overall project cost accurately. Now the problem statement. The first problem is Lisa wants to show that the cost C of the material is C equals to 14x plus 20,000 divided by x. The next problem is the dimension that will minimize the cost. The last problem is the minimum cost. Now for the problem solution. Lisa wants to show that the cost C of the material is C equals to 40x plus 20,000 divided by x. First, the cost C, we will sum all the side of the pool, which is 13x plus 10y plus 10x plus 10y equals to 14x plus 20y. Next, given the area is 1,000 meters square, which means x multiplied by y equals to 1,000. We then move x to the right side, which then we have the last equation, which is y equals to 1,000 divided by x. Now, we have the C equals to 40x plus 20y. We also have the y amount from the area. We then substitute the y into the equation that we have, which then we have the last answer is 40x plus 30,000 divided by x, which means Lisa already showed the cost C material is C equals to 40x plus 20,000 divided by x.
So we will go to the question B. Find the dimensions that will minimize the cost. In this question, we will be solving maximum and minimum problems. There are three steps that we have to do. The first one is we have to find the derivative. The second step is we have to let the derivative equal to 0 and find the value of the variables. And the third step is we have to do the second derivative test. This step is important in order to determine if second derivative is a minimum or maximum value. If second derivative is bigger than 0, then it will become minimum values. Else, if second derivative is below than 0, then it will become the maximum values. Let's move on to the problem solution. Step 1. Find the derivative. We just have to write back the equation of C. C equals to 40x plus 20,000x power of negative 1. And then we do the first derivative. It will become dc over dx equals to 40 minus 20,000x power of negative 2. And then we bring x to the below of 20,000. It will become 40 minus 20,000 over x power of 2. Step 2. Let the derivative equal to 0. So just write let dc over dx equal to 0, and then exchange it with 40 minus 20,000 over x square, and then bring negative 20,000 over x square to the right side, move x square to the left side, and then divide 20,000 with 40, so it will become 500. So the last step is move square to the right side to make it square root 500, and then the answer will be 22.36 meter. Step 3. Second derivative test. So we have to do the second derivative test. So it will become d square c over dx square equals to 0 plus 40,000 x power of negative 3, and then bring x power of negative 3 below 40,000. When x equals to 22.36, we can substitute x into the equation. So d square c over dx square equals to 40,000 over 22.36 cube. Then the answer that we will get is 3.58. As we can see, 3.58 is bigger than 0. So x equals to 22.36 is a minimum value. When we get the value of x, we also can find the value of y. So when x equals to 22.36, we just have to substitute 22.36 into x. So y equals to 1000 over 22.36, and the answer we will get is 44.72 meter. Question C. Find the minimum cost. In order to find the minimum cost, we have to use the equation C that we get from the question A, and then we have to substitute x with 22.36. So just write C min equals to 40 in bracket 22.36 plus 20,000 over 22.36 in bracket, and the answer that we will get is RM 1788.85 cent. That's all from me. Thank you.
So for the conclusion, maximum and minimum points in differentiation are important for analyzing functions and optimizing their values. Differentiation help identify these points by analyzing the behavior of a function derivative. The first derivative test identifies interval of increasing and decreasing behavior, while the second derivative test help find maximum and minimum points based on concavity. Differentiation is applied in fields like economics, physics, engineering, and statistics to solve optimization problems and make informed decisions. It helps optimize production level, analyze motion, design structures, estimate parameters, and more. Understanding maximum and minimum points through differentiation enhance problem-solving capabilities and provides valuable insights into function, behavior, and optimization.